Hi everyone and welcome to today's Daily Booster for Chemistry. This is number 5 in our series and we are also focusing on one of those advanced information listed topics. Today's booster is looking at information which is listed on the foundation chemistry, not specifically listed on the higher tier chemistry, but remember there is that lovely little line saying there is no content that will not be assessed, therefore it's relevant for everyone. To start off with then, let's understand what we mean when we talk about an ion. Quite simply, an ion is a charged particle. So that means that it has either a positive or a negative charge of some description. Now, what we actually find is that ions are going to form when atoms either gain or lose electrons. So one of those two things has to happen in order for an ion to form. We do have some nice, easy to remember patterns that we can learn here. First of all, if we're talking about metals, which are obviously on the left-hand side of the periodic table, these will always lose electrons and they will form positive ions. So, for example, sodium, which is in group 1, loses 1 electron to become Na+. If we were going to consider magnesium, for example, it's in group 2, and it will lose 2 electrons to become Mg2+. On the other side, the right-hand side, we have our non-metal atoms, and they are always going to gain electrons, and therefore they become negative ions. So if we consider the example from group 7, we've got chlorine, and it becomes chloride ions, Cl-, single negative charge, because it gains 1 electron. If we were to think about oxygen, then that's going to gain 2 electrons and become O2- ions. Once we've actually formed these ions, what we see is that the different ions will interact with each other. Now, when we've got a structure made up of different ions, then we have this thing called a giant ionic lattice. What that means is we have a large number of positive and negative ions held together in a repeating pattern. So positive to negative to positive to negative, etc. Each of those ions are held in place by these ionic bonds. Now, what is an ionic bond? Well, quite simply, it's a strong electrostatic force of attraction between these oppositely charged ions. The next thing we really need to consider and remember is, when do ionic bonds form? And the simple answer is that if we have a metal and a non-metal joining together, so we've got a reaction between a metal and a non-metal to form a compound, we have got an ionic bond, because metals are going to form positive ions, non-metals form negative ions, and therefore when they all go together, we will have that little repeating pattern of positive, negative, etc. Therefore creating our giant ionic lattice, each of those individual ions held together by ionic bonds. So they can ask us to draw a dot and cross diagram to show ionic bonding. We're going to start with one that's pretty straightforward. We're going to have a little look at lithium chloride. So lithium chloride. Lithium is in group 1 on the periodic table, and if you look it up, you'll find it has the atomic number of 3. Chlorine is in group 7, atomic number 17. So this tells us how many electrons there are. Now, when we're drawing a dot and cross diagram to show ionic bonding, I always think it's easier to start off by actually just drawing the electronic configuration. So start off with lithium, 2 electrons on the first, and then we have our second shell with the 3rd electron. And then if we do the same for chlorine, note the name, dot and cross diagram. If we've used crosses for lithium, we must use dots for chlorine. So we put 2 on the first shell, then we can have up to 8 on the second, and we will have 8, that gives us 10 in total. So we're going to have to add a 3rd shell here. My drawing of shells is quite terrible. And then we are going to have another 7 electrons. So 2 plus 8 plus 7 gives us 17. So those are the atoms. What we're going to find then, in order to become an ion, what's going to happen is the electron from lithium is actually going to be transferred to the chlorine atom. Because lithium has got 1 electron in its outer shell, chlorine has 7, therefore we transfer that 1 electron to the chlorine to give it that full outer shell. So we then need to draw the actual ions. So lithium first of all, we still have our 2 electrons on the first shell, but because that electron has moved, we don't draw that. So we then put it into these lovely square brackets and we write the charge, which is single positive. Lost 1 electron, single positive charge. We then need to do the same thing for our chlorine, remembering to use the dots. So we do our 2, that's a really terrible close. Try not to obviously do that and actually have your electrons on the shells, unlike the way I've just drawn that. And then we have our third shell with our 7 electrons just as above. And then remember we transferred that 1 electron from lithium to chlorine. So we need to draw it as a cross still, because the electron was in lithium where it was crosses that we used, therefore we need to represent it as a cross. Stick it in square brackets and give it the single negative charge because it gained 1 electron, therefore single negative. And that's it. That's how you show your dot and cross diagram for ionic bonding. The next little molecule we're going to look at are literally the little molecules, the simple molecules. Carbon dioxide, water, oxygen, all examples of these. Now, a simple molecule, quite simply, is something that contains only a few atoms. And these are going to be molecules where the non-metal atoms are joined together by a covalent bond. Because the overall molecule is small, they're going to have low melting and boiling points. And this is down to the fact that there are only weak intermolecular forces of attraction. So anytime you're asked about why a substance has a low melting or low boiling point, weak intermolecular forces of attraction is the phrase to use. Third type of bonding is going to be looking at the covalent bond. So we've looked at ionic, we've looked at intermolecular forces. Now we're going to have a look at covalent bonds. And the definition of a covalent bond is a shared pair of electrons. When do we get a covalent bond? Quite simply, when non-metals join together. So if we've got non-metal atoms joining together, between them is a covalent bond, a shared pair of electrons. Covalent bonds, quite simply, are electrostatic forces of attraction between the nucleus of each bonded atom and the shared electrons. And these are strong bonds. So covalent bonds are strong, intermolecular forces are weak. Right, let's have a look at a dot and cross diagram then, and we're going to have a look at the dot and cross diagram for methane, CH4. So we start off with carbon in the middle. Now, carbon actually has an atomic number of 6, 2 electrons go on the innermost shell, and then we can have our 4 on the outer shell. When we're doing covalent bonding, you only need to draw the outer shells. So we just put our 4 there. Then, because this is the second shell, it can hold up to 8 electrons. Hydrogen has the atomic number 1. It has 1 electron in the outer shell, which can hold a maximum of 2. So what we're actually going to see is our hydrogen is going to overlap and therefore share its electron with one of the carbons. We have 4 hydrogens, so that means we see that happening with each of those individual electrons from the carbon. So what we actually have is a structure that, if we do the displayed formula, looks like this. Carbon in the middle, and then a covalent bond, the line, joining each hydrogen to it. And the covalent bond is the shared pair of electrons, 1 dot, 1 cross. We've obviously talked about different models that we can use here, or different ways to represent bonding, and we need to understand some of the limitations of the models we use. If you've actually built these using mods in class, that's your kind of ball and stick model. And what we're not doing there is considering the size of the atoms or the length of the bonds properly. They're massively exaggerated. we're also not considering the fact that electrons are moving, because when we're using a rigid little plastic stick, that kind of suggests that they are static, and they're not, they do move. If we think about our displayed formula, which we just saw on the previous slide, then that has a big limitation in the fact it doesn't show the three-dimensional shape of the molecule. When we are bonding these atoms together in our covalent structures, rather than just simple molecules, some others form these giant covalent structures, which is just where we have many non-metal atoms joined together by these covalent bonds in a repeating regular pattern. Again, because we've got a repeating regular pattern, that is a giant lattice, just a giant covalent lattice in this case. And good examples here are diamond and silica. We then need to consider polymers. Now, when we're talking about a polymer, what we're referring to is something made from many alkene monomers being joined together. In order to do this, they need two conditions, high pressure and a catalyst. And when this occurs, this is addition polymerization. We're literally joining the alkenes together in a big chain. If they ask you to name a polymer, whatever the name of the monomer is, just write the word poly in front. If they ask you what the monomer is, whatever the rest of the word after poly is, just copy that, just leave the poly off. They could ask you to draw displayed formulas. This could come up here or in your second paper. Do notice all we're doing, this is our monomer with its double bond in the middle here. In order to change it into the polymer, just replace the double bond with a single when you redraw it. Put little bonds extending out from the side in brackets with a little n in the bottom corner. Usually what you find is the structure is worth 1, the little n in the bottom corner is worth 1 mark on its own. If we're going the other way, take the brackets away, lose the n, copy everything else, but stick a double bond between them in the middle, making sure you've remembered not to draw those two. If we consider why we've got different properties in polymers, then it's down to the structure that we find within them. So some of them are thermo-softening, like the one at the top here, where we've got the polymer strands, but they're not cross-linked. The other type, thermosetting polymers, have these cross-links which actually hold the individual polymer strands together. So what we find is that the thermosetting polymer with the cross-linking is actually much harder to separate those strands. So that usually gives it much greater strength. Whereas the thermo-softening polymer, think about your carrier bags, for example, they're not cross-linked, and therefore those chains can very easily slide over each other because the intermolecular forces are easily overcome. The last one we need to look at is metals then. Now, all metals except mercury are solid at room temperature, and the atoms are arranged in this giant metallic lattice. So because it's a lattice, they're arranged in a regular way. A giant metallic means there's lots of them together, all metal atoms. The way we typically represent it is this little diagram here. If you're asked to draw the structure of metallic bonding, or if you're asked to describe metallic bonding and they give you a little space to actually draw a diagram, then make sure you are drawing at least 6 positive metal ions. Make sure the plus goes in them. Make sure you label them as metal ions. Then you've got to add your little dots around, and they need to be labelled as your delocalized electrons. That will get you your marks. So if it's a 3-mark question, you've got 2 just from labelling delocalized electrons, metal ions, at least 6 positive metal ions in your structure. And the last mark is for saying that the metallic bond is the strong electrostatic force of attraction between the delocalized electrons and the positive metal ions. You could do it in writing, but I think the diagram and that last sentence is the best way forward. Final thing then, head on over, have a go at today's quiz all about bonding and all the joys of bonding. Once you've done that, if there are any areas you are uncertain on, then obviously you can watch the video on the main channel, or you can use your other revision material to help you really understand this. Do make sure you know how to draw dot and cross diagrams, you remember all the different types of bonding and what they form between, so that you can answer those questions with confidence. Don't forget to join us again tomorrow for our next Daily Booster.